All right, so I will also produce a paper note for those of you who prefer paper notes. All right, so if you do print this off and you have a color printer, this will print off in color for you. If you don't want color, then just choose black and white. So just like in the video, I have two identical waves. Now what this is showing the two waves on the same medium, but individually. So the green wave is traveling to the right, and the blue wave is traveling to the left. So what happens is they interact on the same medium, and what we see is the red wave. All right, so just like before when we added the pulses, I'm just going to make this a little bit thicker. So this is what we would see on the string. Because you can see right here at this point, the green wave and the blue wave have an amplitude, and so they would add up and produce a point there on the medium. And this happens over and over and over again. So right here, the amplitude of the green one is 0, and the blue one is whatever it is, so the point will be there. And if you did this for every single point, okay, so here it's double, but it's a double trough, so it'd be down here, and so on and so forth, you would see the red line, the red wave. And so what this is a picture of different points in time where the blue and the green produce the red one. So right here, again, you can see that the red wave is increasing because the two crests are meeting each other, so it's approaching the maximum. So this one doesn't show them right on top of each other because that's hard to see. So how do we draw a standing wave? Okay, because we do not see these individual waves is what I want to concentrate that I could not show you in the video. But I'll also point out that here, like I pointed out in the video, is there are nodes. There are points that do not ever move. Okay, and what's important to notice is the distance between nodes is half a wavelength, or distance between even antinodes. So this right here would be an antinode because this is the part that flip-flops up and down. So the distance between antinodes is also half a wavelength. Distance between nodes, okay, is half a wavelength. Successive nodes, successive antinodes, what I mean is right beside one another. So a node to a node is half a lambda. So what are the conditions for a standing wave? We need to have two identical waves. And when I say identical, I mean the same wavelength, the same amplitude, and same speed. Okay, so two identical waves traveling in opposite directions on the same medium. Because they need to be interacting with each other. Okay, and that medium could be a string, could be a spring, it could be whatever you say it is. All right, so now how do we solve these types of questions? How can we use this information? All right, so first of all, I do want to point out that you will see standing waves drawn like this. All right, because this is the flip-flop. So here, node, 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 node. These are all the nodes. Okay, here's the antinodes or loops. All right, now so this is the flip-floppy. This is the 0 point where there's no amplitude ever. And so we draw it because we draw the two instances of maximum. Because if we didn't draw that, it would look like a traveling wave. We want it to look like a standing wave. Okay, so how many nodes are there? 1, 2, 3, 4. There's 4 nodes in this picture. What would we need to know to find the speed of the standing wave or even traveling waves? Because we actually know some information about both of them. Well, to know the speed, we need to know the frequency and the wavelength. All right. What is the aspects of the standing wave? So we need to know frequency and wavelength, which wavelength we could find from the picture if I gave you some measurements. What I should just take out what is. What aspects of the standing waves are the same compared to the two traveling waves? It's the wavelength, which we pointed out in the video, because the amplitude is double, right? What aspect of the standing waves are different? Well, the amplitude of the standing wave is double the traveling waves. Okay. So if I put in a couple measurements here and just made them up, let's, figure out what it is. So if I told you that the amplitude of the standing wave was 5 meters, and I told you that the distance between here and here was, I don't know, let's say 12 meters. And if I asked you, why don't we find out the amplitude and the wavelength of the standing waves and of the traveling waves? Okay, so let's find the wavelength, because that's going to be the same. Okay, so here is a half a wavelength, half a wavelength, half a wavelength. How many wavelengths are there? There's 3 halves of a wavelength, and that's equal to 12 meters. So hopefully you're getting good at rearranging equations. We multiply by 2 and divide by 3, because the 2's on the denominator. We want to get rid of it. We want to multiply by 2. So why don't I go up here where I have some space? Okay, so lambda equals, I'm going to go 2 times 12. I'm going to divide by 3. We probably could do this in our head, because 12 divided by 3 is 4, and 4 times 2 is 8. So that means the lambda, or the wavelength of both the traveling and the standing wave, is 8 meters. So what about the amplitude? Well, just right here from this, we can see that the amplitude of the standing wave is 5 meters. But the amplitude of the traveling wave would be 2.5 meters, because it's half of that. Because essentially at this point, I'd have 2 waves. Okay? I'd have 2 waves acting here at the same time, and that's producing double. All right? So the other sheet that is attached, I'm sorry for how fat this is. I tried to enlarge it for you, and everything got all bulky. All right? So let's solve some other questions. How many wavelengths are shown in the pattern? I'll let you guys do that one. I already did that one. Or something very similar. I'm going to pick something like number 6. So I can do one that's a little bit more challenging, and then your homework is to do the rest of this sheet for today. Okay? Standing waves are set up on a 25 centimeter long string. So here's a string that's 25 centimeters. If the source makes 120 vibrations in 30 seconds, calculate the frequency of the waves on the string, the wavelength of the waves on the string, and the speed of the waves. All right, so from 120 vibrations in 30 seconds, I can get the frequency. So the frequency, okay, is the number of vibrations divided by the time. And that is going to be 4 hertz. Okay, so now I know the frequency. To get speed, I need to know frequency and wavelength. So how do I get the wavelength? So A is frequency, I'm done. And there's no rounding or anything there. Now the wavelength. So they've drawn a picture here, and this is a standing wave. So how many wavelengths are there? Or we can count half a wavelengths. But here's 1, 2, and a half. Or 1, 2, 3, 4, 5 halves. So either way, it's going to be 5 halves of a lambda is equal to 25 centimeters. Because the length of the string from end to end is 25 centimeters, and the amount of waves, or wavelengths, is 5 halves. So again, I'm going to multiply by 2, which gives me 50, and then I'm going to divide by 5, because I'm solving for lambda. Lambda is like x in this case in math. So lambda is equal to 10 centimeters. So now I've done B. The wavelength of the waves on the string is 10 centimeters. So what's the speed of the wave? Well, the universal wave equation is V equals F lambda. So F is 4 hertz. Lambda is 10 centimeters. And so I'm going to multiply this and I'm going to get 40. And if you maybe forgot, hertz is per second. So that's going to be centimeters per second. So the speed of my wave is 40 centimeters per second. I don't need a vector, it's speed. Now there are answers at the bottom of the page. I think that they're mostly correct. They're upside down. I'm hoping this is readable for you guys. It's readable for me, and I've got older eyes than you. All right, if we want to meet, you can meet me on Google Classroom, and that's your lesson for the day, standing waves. Bye-bye.